You know, in the world of electrical engineering, there's this tool that's both incredibly powerful and, let's be honest, a little intimidating at first. It's the time current curve, or TCC. This one graph tells us the complete story of how a protective device will respond to any kind of overcurrent. So in this explainer, we are going to demystify this chart and show you how it becomes a clear roadmap for a safe, reliable electrical system.
So here's our game plan. First, we're going to get our feet wet with the absolute fundamentals, just learning to speak the language of the curve. Then we'll dissect a modern breaker curve, piece by piece, to really see how it works. We'll pit that against the simple fuse, and then the main event. We'll see how to make them all work together to achieve proper system coordination. And to wrap it all up, we'll talk about some real-world design tips and common mistakes you definitely want to avoid.
Okay, so let's start at square one. Before we can really make sense of these curves, we've got to speak the language, right? That means getting comfortable with the graph itself, what each axis represents, and why in the world it's set up the way it is. So you might be looking at this grid of lines and thinking, why all the fuss? It's just a graph. Well, here's why it's so important. Every single line you see on this chart represents a split-second decision that protects incredibly expensive equipment, and more importantly, it protects people.
Think of it this way. A well-coordinated system, the kind we can visualize with these TCCs, is literally the only thing standing between a normal day and a total disaster. It stops expensive gear like transformers and motors from getting fried by overcurrents. It makes sure that everything from a small overload to a massive short circuit gets cleared safely. And this is huge. It minimizes outages. It keeps a small problem in one corner of the building from taking down the entire facility. And by clearing faults in milliseconds, it drastically reduces the terrifying energy of an arc flash. So yeah, mastering the TCC isn't just about graphs. It's about mastering system safety itself.
Okay, let's break down the actual graph. The vertical axis, the y-axis, is time, measured in seconds. The horizontal axis, the x-axis, is current, in amps. Now notice they are both on a logarithmic scale, and this is absolutely crucial. This log scale is what lets us squeeze an enormous range of events onto a single page, from a tiny overload that might last for minutes, all the way up to a catastrophic fault involving thousands of amps that has to be cleared in just a fraction of a second. All right. Now that we've got the lay of the land, let's get our hands dirty. We're going to dissect the most common type of curve you'll run into, the one for a modern electronic circuit breaker. We're going to look at each protection layer, one by one.
This first part, this sloped region, is called the long time function. This is your workhorse for overload protection. We're talking about situations where a circuit is drawing, say, 10 or 20% more current than it should, maybe from an overloaded motor. The magic here is what we call its inverse time characteristic. Look at the slope. For a small overload, way over on the left, the breaker might wait for hundreds of seconds before tripping. But as that overload current gets higher, moving to the right, the trip time gets faster and faster. Why? Because this curve is designed to hug the thermal damage curve of the cable it's protecting. The more current, the faster a cable gets damaged by heat, so the breaker has to react faster to save it.
Okay, moving on. Next up is the short time region. This is for handling more serious faults, not quite a dead short, but definitely more than an overload. It has a pickup setting, which is just the current that wakes it up, and a delay. Now, you might be asking, why would you ever want to delay a trip during a fault? It sounds crazy, right? Well, it all comes down to one critical word: coordination. That tiny, intentional delay is just enough time to let a smaller breaker downstream handle the problem first, so you don't cause a much bigger outage than necessary. And then, for the absolute worst-case scenario, we have the instantaneous region. This is the breaker's panic button. This is for massive fault currents. We're talking a direct, metal-on-metal short circuit, what some people call a bolted fault. When the current hits this level, there are no more delays. There is no waiting. The curve just drops to a flat horizontal line at the bottom, and the breaker trips as fast as its mechanical parts can physically move. This is the ultimate defense against the destructive force of a major fault.
Now, on top of all that, many breakers have another layer of protection specifically for ground faults. A ground fault is when current leaks out of the normal circuit and finds a shortcut to ground. Now, these can be incredibly dangerous, but the tricky part is they often involve a lot less current than a big short circuit. That's why the ground fault curve, as you can see here, sits way over to the left, in the low current region. This special sensitivity allows the breaker to see and clear these sneaky, low-level faults that the standard protection functions might not even notice.
Okay, so we've gotten pretty deep into modern breaker curves. But what about the OG of protection, the humble fuse? They essentially do the same job, but when you look at their curves, you see they are two totally different beasts.
So take a look at the TCC for a typical high-capacity fuse.
what's the first thing that jumps out at you? It's the shape, right? Instead of all those adjustable steps we saw with the breaker, the fuse has just one smooth, continuous curve. Its behavior is dictated entirely by the physics of the metal element inside it melting, and that means this curve is completely fixed. You can't adjust it. A fast-acting fuse will just have a steeper curve than a time delay fuse, but you can't change it once it's made.
So when you put them side by side, what's the real difference? Well, it really boils down to this. Fuses are simple. They have one job and a fixed curve. When they do their job, they sacrifice themselves and you have to replace them. Breakers, on the other hand, are complex and highly adjustable. They give you the power to fine-tune your protection scheme. And of course, you can just reset them. That flexibility and precision is why they generally have a higher initial cost.
Okay, we've learned the parts. We understand the players, breakers and fuses. Now let's put it all together and talk about the ultimate goal of any TCC study, system coordination. This is the art of making sure all your devices play nicely together.
The name of the game here is something called selectivity, or sometimes you'll hear it called discrimination. And the idea is actually pretty simple. When a fault happens, you only want the protective device that's immediately upstream of the problem to open. That's it. It's like having a chain of command. You want the soldier closest to the fire to handle it. You don't want the general at headquarters to launch every missile. For an electrical system, it means a tripped outlet in the break room shouldn't take out the power for the whole floor.
Look, if you remember just one thing from this whole section, let it be this. The device closest to the fault should always trip first. This is the golden rule. It's what contains the problem, minimizes the outage, and keeps the rest of your system running. Every single adjustment you make in a coordination study is to serve this one simple goal.
Now this is what we're aiming for. This is what a beautifully coordinated system looks like on a TCC plot. The red curve on the right is our downstream device, the one closer to the load. The blue curve on the left is the upstream device. See that nice, clean, white space between them? That's our safety margin. It means that for any fault current along the bottom axis, if you draw a line straight up, you will always hit the red curve long before you get to the blue one. That time gap is everything. It guarantees the downstream device will win the race to trip every single time.
Now, there's another term you'll hear called cascading, or backup protection. This is a bit of a special case, so listen closely. Sometimes you might have a situation where the potential fault current is so massive that it's actually higher than what a smaller downstream breaker can safely handle. In a cascading system, a bigger upstream breaker is specifically tested and rated by the manufacturer to help out. It acts super fast to reduce the fault energy, basically giving the smaller breaker a chance to survive and clear the fault. But, and this is critical, this is an engineered system that has to be tested and approved. It's not a substitute for good selectivity.
All right, let's move from the ideal world of graphs into the messy reality of design. Because knowing the theory is one thing, but avoiding the common pitfalls is what really makes a system safe and reliable when it counts. So where do people usually go wrong? Well, here are some of the most common blunders. The number one mistake is having curves that overlap or cross. That's a total failure of selectivity. You have no idea which device will trip first. Another big one is setting an upstream breaker's instantaneous pickup too low. It gets too sensitive and trips for faults that a downstream breaker should have handled. Then there are the things people forget to plot, like the huge but temporary inrush current when you energize a transformer, or the starting curve of a big motor. Ignoring those leads to constant, frustrating nuisance trips. And finally, getting the phase protection perfect but completely forgetting to coordinate the ground fault curves can leave a huge, dangerous hole in your safety net.
Okay, take a look at this. This is a textbook example of poor coordination. That green curve represents the starting current and overload protection for a motor. The black and red curves belong to the main breaker feeding it. See the problem? Right there, where the curves cross. The motor's own overload protection is sitting on top of the trip region for the main breaker. This means a perfectly normal overload on that one motor could end up tripping the main breaker, killing power to a whole bunch of other equipment that was working just fine. That is a coordination failure.
All right, we have covered a ton of ground, so let's just boil it all down to the absolute key takeaways you need to remember. First, TCCs are not just pictures. They are fundamental design tools. Second, never guess. Always use the specific TCC datasheet from the manufacturer for the exact model of the device you're using. Third, remember that all this work has two goals: increase safety and minimize downtime. And finally, it all comes back to that golden rule. Your number one job is to isolate the fault to the smallest possible part of the system. So there you have it. We've gone from decoding the basic language of the graph all the way to the fine art of coordination. You now know how to read the story that a protection system is telling, so the only question left is, what story is your system telling? Is it a story of carefully planned safety and reliability, or is it a story of hidden risk?